Okay, so atomic size, well, atomic size, how big is an atom, right? But you run into a problem if you're trying to measure across an atom. Well, the problem is, where do you start measuring? Okay, if you try to measure from one edge of the atom to the other edge of the atom, you'll run into a problem. Because the edge of the atom, well, it's not an edge, it's an electron cloud. It was foggy yesterday morning. Could you have walked, somebody hand you a rope and say, how far is it to the fog? Would you have known exactly when to stop? Because the edge is kind of foggy. Well, the same is true of our electron cloud, right? It doesn't have a definite edge. Okay? So if it doesn't have a definite edge, you don't know where to start measuring. Well, you could get one end. You could measure the nucleus, because you know where that's at, but you still wouldn't know where the other edge, the outside edge was. You could try for a radius, but that wouldn't work either, because you know where the center was, but not where the outside edge is. So if you can't figure the outside edge. So they get around this by not measuring one atom. They don't measure one atom at a time. They measure two atoms at a time. Well, how's that going to solve the problem? If I can't measure how big one is, how am I going to measure how big two are? I can't tell how big one is. How am I going to tell how big two are? Well, here's the answer. You're going to do a little bit of geometry. If I take two atoms and put them together, and I measure the distance between their nuclei. Think about geometry, that would be a diameter. Okay? So what they've decided is to call the radius half the distance between two nuclei of a molecule, where the atoms are stuck together already. An atomic radius is a way of measuring the size of atoms. A bigger atomic radius would be a bigger atom. Smaller atomic radius would be a smaller atom. Now, if you look, the circles aren't perfectly round in the middle. They overlap each other a little bit, so it's actually the radius that you get this way is a little bit too small, but it puts them all in the right order. So see how that solves our problem? I don't have to measure the edge. I just have to measure where the two pieces that are solid, that are got some mass. I can find those two pieces. Take that distance between them. That would be a diameter. Half the distance would be a radius. Okay. So that's what they're measuring when they measure atomic radius or atomic size. Okay. So the trends. And the trends are going to be influenced by two factors. A factor that takes place in groups and a factor that takes place in periods. First one that's going to influence is energy level. Higher energy level is further away. Higher energy level is bigger atom. And the other one would be the charge on the nucleus. The reason why the electrons stick around is because the nucleus has an opposite charge and opposites attract. Opposites attract, more opposites attract, more opposites attract more. So the more protons I put, the more. So that gives me two competing things. One thing tends to make the atom bigger, more energy levels. The other tends to make the atom smaller, more protons pulling. Okay. So if you look at it, it gives us this trend. And when you graphed it, you connected the ends of them one to the other. Here I just did each period by itself. So period 1's the bottom and period 5's the top. Okay. So each one of those lines is a period. What is the general trend in size? So as I start high, I end low. The general trend is a decrease, right? So atoms get smaller as you move to the right across the table. And that's kind of surprising. What that's saying is lithium with 3 electrons is bigger than neon with 10 electrons. It's got over 3 times the electrons, but neon's smaller. Why? Well, as I go across the period, lithium is in the second energy level, 2s1, and it's pulling in that second energy level with 3 protons. Beryllium's pulling in that same energy level in with 4 protons. 4 protons is going to get you a better job. Neon, it's 2p6, but it's still 2. It's still the second energy level. But it's being pulled with 10 protons. 10 protons is going to pull better than 3 protons. So as I go across the row, it's not shielding, it's not energy level, it's different. We're in the second energy level all the way across. The period is about energy level. But there's more nuclear charge. Here the second energy level is being held with 3 protons, there it's being held with 10 protons. That's going to pull those outermost electrons in closer, which means the atom's going to be smaller. Extra charge pulls more, pulls those electrons in closer. So when we started this, I started off with the Y part. The Y in periodic trends is always about nuclear charge. Okay? So it's always about protons pulling more. The group trend. There's a group trend in radius. What's the general trend? As we go down a group, the atoms get bigger. Because left side is the top of the table, right side is the bottom of the table. As you go down a group, the atoms get bigger. Now, is there any place where that's not true? Well, actually, there's a place right here. It got smaller right there, right? Why would it have gotten smaller? Well, that's period 3. Sorry, that's group 3A. Okay, it's group 3A. What's going on with group 3A? Well, the first one in group 3A is boron, then aluminum. But notice that before I can put gallium in, I've got all these extra electrons that have to go into a lower energy level. Okay? So my energy level goes up 1, but I don't go up. Here I went up 8 protons. Here I'm going up 18 protons. 18 protons is going to pull more. So the difference between this atom and that atom is 10 protons. So that's why that one drops. It's because you're not talking about the Ds. We don't try to pretend what's happening in the Ds. I didn't have you graph any of the transition metals. So why do they get bigger? Because you're adding an energy level. Another way of saying that you're adding an energy level is that you've increased the shielding so that that outermost electron isn't attracted. It's not attracted and get further away. So, now you graphed leaving the D's out. Here's what the graph looks like if you leave them in. Oh, I left one off. I left helium off. Okay, so helium's going to be right next to hydrogen here, but is it going to be higher or lower than hydrogen? As I go across, hydrogen's pulling that first energy level in with 1 proton. Helium's doing it with 2. Twice as many protons should pull more. So more pull means helium should be down here. Okay? So this part right here, you didn't do this part. Now this part you did, and this part you did, but you missed all of those. Well, not quite all of those, but a bunch of those, because that's where the D's are filling up. Okay? They don't follow a nice pattern. That's why they're not representative elements, because the pattern is not well represented. Okay? So the same thing happens here with the D's. Okay? So we don't try to predict the D's. Only the S's and the P's. Only the representative elements are we expect to be able to predict. Okay? So, where's the biggest atom? Well, the biggest atom is going to be on the bottom and on the left. Now, we might be tempted to say, so that would make, come on, piece of junk. Why do you say there's something else clicking there? Okay. So, say they didn't fill in this one. The reason why is because they've only made 3 or 4 atoms of it, so they can't really tell us how big it is. Actually, no. This is hydrogen, lithium, sodium, potassium, rubidium, cesium. Oh, francium. Now they actually know. They know how big francium is. And so it's going to be the biggest atom. If we had to predict the biggest atom to be francium, but you're never going to see it. That's because at any given time, in and on the Earth, there is 1 gram of francium. Total. Except every kind of francium is unstable, so it falls apart. And it has a half-life of 20 minutes. So there's always 1 gram of francium, because stuff decays and turns into francium. But then that francium decays right away. So there's always 1 gram, but it's not the same 1 gram. But after a couple hours, just about every francium atom you started with would be gone. Because we cut in half every 20 minutes. You start cutting in half 5 or 6 times, it gets really tiny. Okay. So smallest atom, helium. Okay. So, which one of these is larger in size? Oxygen, sulfur, selenium, tellurium, or polonium? After you find the second one, the rest are easy to find. Okay, so what you need to think about, what kind of trend is this? Is this a group trend or a period trend? Group. So it is a group trend. The further down I go, the more layers. So that's going to make the atom bigger. So the biggest one would be on the bottom. It's a Poe choice. Which of these is larger in size? Potassium, gallium, arsenic, bromine, or krypton? This one takes a little longer before you notice it, but say, oh, those are all in period 4. Right? They're all the same row. So the largest radius would be the one with the fewest protons in that row. So potassium is bigger than chromium, or krypton, even though krypton has almost twice as many electrons. 19 to 36, that's almost twice as many. Why? Why is K larger than Kr? Well, the answer is I'll pick the only one that's actually a true statement. Does Kr have more energy levels? No, because it's 4s1 and 4p6, right? So it has the same energy levels, so not only does K not have more, krypton doesn't have more. So that gets rid of 2 of my answers. And which has more protons, krypton or potassium? Krypton. So why is K larger? Because krypton has more protons, which pulls it in closer. Or you'd say K has fewer protons, which doesn't pull it in as well. Make sense? How did we do this? Okay. Everybody see that that's where they're at on the table? So which one's going to be larger? Is it going to be at the top or the bottom? Bottom. Is it going to be at the left or the right? Left. So that would be gallium. Right? Now, which would be bigger? Aluminum or germanium? Ooh, this one's a little tougher because I know that gallium is going to be bigger than germanium, but I also know that gallium is going to be bigger than aluminum. So I know they're both smaller than gallium, and I know that they're both bigger than silicon. But what does that tell me about the order of aluminum and germanium? Nothing. It's hard to compare this way. You can always make the comparison on that diagonal, but going the other diagonal, it's hard to compare. You actually have to go look up numbers. Unless they're way far away, one's way over here and the other one's way over there. Does that make sense? So that is the what and the why of the periodic trends in size. Okay? That's what I expect you to know about periodic trends. What they are and why they happen. Okay? And the why is always the same for all the trends. Just got to remember what the trend is. Second trend, we're going to talk about ionization energy. And ionization energy is the energy to take off one electron. Okay. Now, when we did atoms earlier this year, we talked about how to figure out protons, neutrons, and electrons. And I was always careful to say that the atomic number was the number of protons, and that equaled the number of electrons because the atom is neutral. Right? I never said atomic number was was electrons. I always said it was protons. Okay? That's because I can move the electrons around. What am I going to be left with if I remove an electron? Well, let's take sodium. Sodium starts off with 11 protons and 11 electrons. If I take an electron off, it still has 11 protons, 11 positive pieces, but now it only has 10 negative pieces. So it's got an extra positive piece. So we call it 1 plus charged. It has a 1 plus ion. So when an atom has a charge, it's no longer called an atom, it's called an ion. Okay? And the energy to do that, well, if we're taking off just the first electron, it is called the first ionization energy. If they don't tell you which ionization energy it is, it's the first one. So we start with the neutral atom, and we take away an electron. We're left with the 1 plus ion. And the reason why we write it as 1 plus is so we think of it as one extra positive piece, not so we don't think of it as an exponent that we are doing math with. So by writing 1 plus, you're emphasizing the pieces that are extra. Okay. Now, you can take another electron off. Okay. And you have to put some more energy in to take that second electron off. Now they want to name that the energy to take that second electron off, but they got their choice. So they wanted to call it the energy to take off 2 electrons, or the energy to take off the second electron. Understand the difference between those two? Because either one would seem valid. They picked the one that gave them more information. Second ionization energy is the energy to take the second electron off. So after you put in the energy to take the first one off, you put in more energy to go get the second one. Now the first electron, I took it away from a neutral atom. When I go to get the second one, the thing I'm pulling it away from is no longer neutral. Now it has a positive charge. Since it has a positive charge, pulling something negative away from it is going to be harder. So the second ionization energy is always bigger than the first ionization energy. How many ionization energies do they have? Well, the answer is as many as they have electrons. You can talk about the 92nd ionization energy of uranium. How hard it is to take the 92nd electron off. And what can we say for sure about the 92nd electron? It's going to be harder than the 91st, right? Because I'm taking away from something 90 positive instead of 91 positive, or instead of 89 positive. The third ionization energy removes the third electron, and it's bigger than the second or first. So the bigger what bigger ionization energy you're measuring, the bigger it is. So if we say the 7th ionization energy, that means we've taken the first 6 off already, and now I'm trying to take that 7th away from something that's 6 positive. That's going to be hard to do. Opposite charges attract. More opposites attract more. And this is always true. The first is always the lowest. The second's always highest. The third is higher. The third is always higher. Fourth is always higher. The fifth is always higher. But it's not actually smooth transitions from one to the other. It's kind of big jumps along the way. Well, what do you mean by big jumps? Well, let's look at this table's in your book. You don't have to cover, but I just want to point out something. In every case, the second is bigger than the first, and the third is bigger than the second. Every single time that's true. But here, carbon had about doubled to go there and about doubled to go there. But if you look at lithium, it starts off with the lowest first ionization energy and is over 10 times as big for the second. And the third doesn't quite double. Whereas beryllium, the first one doubles and the second one is 8 times higher. I go from 1,700 to 14,000. There's some big jumps along the way. Okay? We need to be able to explain those big jumps. Why is it so much harder to take the third one from beryllium than the second one? I mean, and actually, you'll find that the highest one in each row is immediately followed by the lowest one in each row. Isn't that strange? There's got to be some reasons for those patterns. There's got to be something going on with the atom. This is going to tell us about. This tells us about how the atoms put together. Okay, but so what determines ionization energy? The same things that determine size. The greater the nuclear charge, the greater the ionization energy. More positive pulls more. The more it pulls, the harder it is to take off, the more energy you have to put in. The other thing that affects size is shielding, or energy levels, right? Increased energy levels, increased shielding, decreases the ionization energy. And here, we're actually going to run into the reason for some exceptions along the way. Okay? And it's the same reason for the exceptions as last chapter. Half-filled orbitals are low energy. So making them is easy. You'll have a lower ionization energy to make them. So if you got something that by losing one electron gets to be full, or one electron gets to be half full, take it off, you end up full, take it off, you end up half full, then that electron's going to come off easier than it normally would. So want to look at it in terms of groups and periods. One's easy to explain, one's a little harder, so I'll do the easy one first. The group trend. There's the group trend. What can you say? What is the trend? As you go down a group, it decreases, right? So the lower down the group, the lower the ionization energy. Why? Because every time I go down, I'm adding a layer between the nucleus and the outside electron. I get more shielding, more energy levels. That outer electron's less attracted. Okay, to give you an analogy, it's not a perfect analogy, but it gives you an idea. The magnet is attracted to the refrigerator. But you come home from school with a picture You say, oh, Mom, that's lovely. Your mom says, that's lovely. She sticks it on the fridge with a magnet. The next day, you come home with another picture. Oh, it's beautiful. Takes off the magnet, puts the next picture up, sticks on with the magnet. After a while, all the papers fall on the ground. Because the more papers you put in between the magnet and the fridge, the less attracted the magnet is. The more layers of electrons I put between the inside and the outside, the less attracted that electron is. The easier it is to take off. The lower the ionization energy. That's what this graph is showing. That you've got extra layers, so it's easier to take them off. All right? So think about magnets sticking to stuff. Extra layers would make it come off easier. Okay, here's the periodic trend. So what's the general trend? Well, it starts out low, ends up high. It's an increase. Is it a guarantee? Nah, but it's a trend. Right? Trends aren't guarantees. Past performance is no basis for future expectations. Okay, so we're doing by period. All the atoms are in the same period. All the atoms in the same period have the same shielding. So I'm not adding layers. I'm adding magnets. Does that make sense? I'm not adding layers, I'm adding magnets. So the further across I go, the better attracted it is. That nuclear charge, increasing nuclear charge, every proton's like another magnet. It's going to stick a little bit better. Until I put a whole other layer of papers underneath it. So our general increase is caused by extra nuclear charge. You can see there are two places where there's exceptions. It decreases in 3A and it decreases in 6A. Why? Why does it break the rule? Why does that electron suddenly become easier to take off? Well, there's a couple ways of explaining it. I talked about one of them already. Think about electron configuration. In group 3A, everything is going to end in S2P1. Everybody agree? And what happens if you take away an electron? You're left with S2. S2 is full. It's easy to make things that are full. Okay, and 6A is here. So that would be S2P1, 2, 3, 4, S2P4. And if I take an electron away from that, I make it S2P3, and P3 is half filled. Half filled is easy to make. Yeah. So you got exceptions at the P1 and the P4 orbitals, because it makes things full or half full. I can give you another reason why that half full would be a little bit more stable. It's S2P4, right? So that is S2P4. 1, 2, 3, 4. Look at where the electron is. It's next to another electron. It's being pushed by that other electron, which is going to make it easier to remove. Obviously, that pair means they're in the same space. If they're in the same space, one's going to push the other one out. So it's going to be easier to take off. Make sense? Okay, so let's look at the whole pattern and stop and think about it. So, helium has a higher ionization energy than hydrogen. Why? Well, the first thing you have to do is go and find out where they're at on the table. You'll find that they're both in the same row on the table. So now I'm talking about a period trend. Since they're in the same row, they have the same shielding. But helium's got twice the protons as hydrogen. Helium's got a greater nuclear charge, so it's going to be harder to remove that electron. So if you remember that ionization energy is about pulling electrons off, it's easy to explain all these things based on more attraction from protons, less attraction from extra levels. Okay, the next atom is lithium. Does it make sense to compare lithium to helium? No, what should I compare lithium to? Lithium. No, lithium I should compare to hydrogen. See, I can compare lithium and hydrogen. They're in the same group. Okay. So where's lithium going to be? Well, as I go down a group, I add energy levels. So energy levels make it easier to take off. Extra papers make the magnet easier to pull off. Because it's got a shield. Hydrogen didn't have a shield because there's only one layer of electrons. And that extra shielding outweighs the greater nuclear charge. I mean, lithium has 3 times as many protons, but the shielding blocks more than 2 of them. The shielding wins out over the nuclear charge as you go period to period. Okay. Next is beryllium. Beryllium should be higher because it's got same shielding, but a bigger nuclear charge. So they're both in the second energy level. Lithium are trying to pull away from 3 protons. Beryllium are trying to pull it away from 4 protons. 4 protons is going to be harder to pull it away from. Next on the list is boron. So boron has got the same shielding. It's got a bigger nuclear charge. So of course boron is high. Oh, boron's not higher. Why not? I mean, it should be. It's got the same shielding and the bigger nuclear charge. It should be higher. Why isn't it? Well, by removing that electron, I make a full s orbital. And that's easy to do. So that's where our exception happens. Next comes carbon. Same shielding, bigger nuclear charge, so it's higher. Nitrogen, same shielding, bigger nuclear charge, so it's higher. Oxygen, same shielding, bigger nuclear charge, so it's not higher. Didn't work that time. Why not? Because by removing it, I end up with a half full. Oxygen is P4, take 1 away, you're at P3. P3 is easy to make and hard to break up. Then after oxygen comes fluorine, same shielding, bigger nuclear charge. And then neon. Neon's going to be bigger than fluorine, but how is it going to compare to helium? It's got to be higher than fluorine because of the bigger nuclear charge, but it's got to be lower than helium because of the shielding. So neon's a little bit lower than helium. Okay, next is sodium. What should I compare sodium to? Well, it makes sense to compare sodium to lithium. Extra shield means less attracted. Okay, sodium's way down here. And here's what the D's do. Okay, not as predictable. They all stay about the same. But look at sodium. Sodium was way down here. It was really easy to take an electron off of sodium. Because if you take one electron off of sodium, it ends up at a full energy level. Okay? It ends up at a full energy level. Full energy levels are really stable. So that's the pattern in first ionization energy. So which of the following would have the lowest ionization energy? Because Homer's going to ask you questions like this tonight. But have your seats, folks. It's not, the bell doesn't dismiss you. It's not a race. Okay? So which of these would have the lowest ionization energy? Would be at the top or at the bottom?
Daniel Sanchez, please report to the administration office.
Ionization energy increases up and to the right. So the lowest ionization energy would be the one at the bottom left, which would be rubidium. They're all in the same period. Okay. One with the least charge in that period. Okay. Homework tonight, if you got to work on those graphs, do that so I can get them graded. Have a good one.